All right, ladies and gentlemen, welcome to the next episode of the Simpkins Physics Corner. Today we're going to be looking at a conservation of energy problem, and we've also introduced oscillators and simple harmonic motion. And so a little context to this, if you can imagine, if you take a rocket and you attach it to a spring, if I were to take this and push it back a little bit, then I'm storing energy inside that spring. Now, of course, when I release said spring, the rocket is going to take off, and as the spring does work on the rocket is going to gain kinetic energy. Now, in any oscillating problem, there's always a special place called equilibrium, which is where the forces are equal. Now, one thing you have to understand about this spring is that right now it's compressed in this direction, and then as it reaches this equilibrium position, it's going to be relaxed or not exerting any force. And then as the rocket passes that position, it's going to be again exerting a force, but now in the opposite direction, so back that way. And you can imagine the rocket would bounce back and forth, back and forth. Oh, it would be oscillating, and that's why they call it an oscillator or simple harmonic motion. So let's go ahead and take a look at setting up this problem. Of course, before I even read, I'm just going to circle any number that I see in the problem. You don't have to be even literate to start a physics problem. Now let's go ahead and take a look. A model rocket has a mass attached to it, so I'll just write the mass over here. I'll label my diagram. And the spring has a spring constant that's written as the variable K of 6 newtons per centimeter. The spring is compressed by 18 centimeters as shown in the diagram here, and then released. All right. The intent is to shoot the rocket horizontally, but the release mechanism fails to disengage, so the rocket starts to oscillate horizontally. So basically it stays attached. Ignore friction and assume the spring to be ideal. What is the amplitude of the oscillation? All right, so first some definitions. Amplitude in simple harmonic motion is simply the distance that you are displaced from the equilibrium or rest position. Now this, it actually tells us it's compressed by 18 centimeters, and since our diagram shows that we're relaxed right here, our amplitude for this problem is actually going to be 18 centimeters. So, woohoo, we already saw in part A. It's really easy. So that's part A. The amplitude is 18 centimeters. You just have to know the definition of amplitude is the displacement from equilibrium. I'll draw that up here real quick for you guys just so you can remember that. Let's say you have a spring, and this is its relaxed position, and then in this problem we've compressed the spring now. My spring got straight, but there we go. This distance right here would be called big A, or amplitude. You can see how we've moved the mass here. We've compressed the spring, and we've moved it back a certain distance. That's called the amplitude. Part B, what's the maximum speed? So it's at this point that you see in this problem, how in the world am I going to find speed? Well, we know that when we compress a spring, we're storing energy. Okay, so that means over here we have some spring potential, US, potential in the spring. And then after we release the spring, as the rocket whips through the equilibrium point, we know that at equilibrium the spring is exerting zero force. It's because it's in equilibrium. And so if there's no spring force, then right here at the equilibrium position, the rocket has all its energy in the form of kinetic energy. And what we can say for certain is that the initial stored spring energy is going to be equal to the kinetic energy as the rocket passes through the equilibrium position. The reason we can say that is not because spring is equal to kinetic, but it's because the total energy at the beginning, which just so happens to be all potential, is equal to the total energy at the equilibrium position, which just so happens to be all kinetic. So for part B, as we go to set this up, we're going to say the stored potential energy in the spring, and I'll just put, I'll put at point 1, we'll call this point 1 over here, is equal to the kinetic energy at point 2, and I'll call this point 2 in our diagram there. Okay, so we're saying that this potential here is equal to the kinetic here. Now we're just going to go ahead and re-express this with our equations that we know. So the equation for the potential energy stored in a spring and the equation for kinetic energy. All right, and we'll go ahead and plug in our known values. So from our problem, this is our K up here. We've also labeled it in our diagram, which is helpful. So I'll plug it in as 6 newtons per centimeter. I don't know why I like switching those. Times our compression distance. Okay, X is the compression distance. In this case, we've compressed our spring 18 centimeters. So we'll go ahead and drop that in there. Equals 1/2 mass, which is conveniently 1 kilogram for this problem, times V squared. Okay, so what we've just done is we've used the conservation of energy to say the spring potential at the beginning is equal to the kinetic energy at the equilibrium point, because it's the only types of energy we have at these two locations. And if we could do some algebra here, I'll go ahead and grab my calculator. I did remember it this time. All right, so 6 times 18 squared. You notice, actually, there's a 1/2 on each side, so I'm just going to go ahead and cancel those and make my life a little easier. And 1944 newtons is over here, but it's kind of odd. It's newtons centimeters, which I know is weird, but it's units. Over here, we have 1 kilogram, so that just kind of goes away, and our big time fatal error. Anytime you are doing a physics problem, you should always get into standard international units as soon as possible, which means centimeters are out of the question. Because you notice when we get to this point, we have newtons times centimeters divided by 1 kilogram. What unit even is that? That would be 1944 meters per second squared times centimeters. Oh yeah, meters, centimeters, all the time, right? Well, okay, maybe not the best idea. Now, if we keep in mind that 100 centimeters is equal to 1 meter, we might be able to shrewdly take care of this. You could avoid all of this nonsense if we just put our distance or our compression distance in meters and our K in newtons per meter right from the very beginning. But since we're here, we've already done all this work, we can be a little shrewd here. All right, so that's going to be equal to v squared. So this is going to be a bunch of nonsense unless we take care of these centimeters. So given the idea that 100 centimeters is equal to 1 meter, what that means is that our value over here is actually going to be 19.44 meters squared per seconds squared equals v squared. And we come in for the diving save at the last minute. Now, we could have avoided that last minute dive if we would have just taken care of our units from the very beginning. I'm going to move this up here because we're running out of screen space here. If I take the square root of 19.44, I find that my velocity through the equilibrium position is 4.4 meters per second. So that would be our velocity as our cart comes whipping by the equilibrium position. If you want to see a video about what to do for part C, you got to tune in next time, because the added challenge here is we're at a place where it's not all potential or all kinetic. It's somewhere in between.